All right, hi everyone. I think this is the second last week now. We are going to do the end of this one. So we're going to look at the questions, the exam type questions based on enzymes. We'll go through carbohydrates. And if we have time, we'll also do plastic polymers as well. So there'll be this one and one more to do in the holidays, and then probably a what's the word? A bonus one that I'll do as well. So hopefully everybody had a go at these questions. So we have inorganic catalysts and enzymes, which are organic catalysts effectively. For those of you who might have done particular topic for your assignment, you'd also know that there are organic catalysts as well. Ross, you would have done one of those. So there's actually three kinds: organic, inorganic, and enzymes, because you can have an organic catalyst that is not an enzyme. Anyway, so they both lower the activation energy. That's the whole point of a catalyst. Which one is highly specific? Lachlan's here. Hi, Lachlan. So is an inorganic catalyst or an enzyme highly specific? Which one, or both? Can you see the slides? I'm not sharing the wrong thing. Okay, so only an enzyme is specific. An inorganic catalyst and an organic catalyst can catalyze a broad spectrum of reactions. Only an enzyme is made of proteins. Neither of them are changed by the reaction. That is sort of mainstay of catalysts. They are not actually used up in the reaction at all. And they both increase the reaction rate. So the active site of the enzyme is where the substrate, which is what's being reacted or broken down or built up, binds with the enzyme. So it's where all the magic happens. We get intermolecular forces happening, and the reaction can occur. So we've got the two models of enzymes. I'm only going to spend like 5, maybe 7 minutes on these questions. We've got the induced fit, which is the active site of the enzyme can change, and the lock and key, meaning one substrate, one active site. It's completely rigid. So the induced fit model does not explain why enzymes do not catalyze a wide range of reactions. That would be the lock and key model. So the enzyme molecule has an active site. I mean, that's for both of them. So the active site does not change shape as the substrate enters. That would be the lock and key model. In both of these, an enzyme substrate complex will form, and the active site is able to form relatively strong bonds with all of the isomers. That's only in the induced fit model. So what we're doing is we're working through more and more complex. So why do enzymes only work over a relatively narrow pH range? Anyone know? It's all with temperature has to do with the shape of the so it's to do with the active site shape. So the shape of the active site is dependent on the strength, on the structure of the protein. When you heat up the protein, you actually change the conformational shape. The pH, the reason it changes with the pH is because we add H plus or add OH minus, it changes the charge on the end of the R groups on the amino acids. Sorry, I had a little moment there. So I won't worry about, if you got the slides, you'll be able to do question 5. So our 4 intermolecular forces, we've got our 3 that I harp on about: hydrogen dispersion and dipole-dipole. Almost forgot then. We then have, we've also got ionic interactions, which are positively and negative charge. So the induced fit model is more accurate, because if it was so rigid like that and you couldn't change or alter, then that's not the most efficient way. And we know that certain enantiomers of substrates can be broken down by the same enzyme. We talked about the temperature range here for question 7. So we're looking at increasing temperature, and then the protein, the active side of the protein, is a certain shape, right? Certain conformation. As you heat it up, the bonds in the protein become weakened. As they do that, the protein changes shape. As the protein changes shape, so does the active site of the enzyme. So Jacob asked about ionic interactions. There's a big difference between an ionic bond between a nonmetal and a nonmetal. An ionic interaction is just between a positive and negative dipole. So you've got COO minus and H plus. Okay, so everything we've spoken about here, enantiomers, the induced fit model, can be used to answer question 8. I want everyone to take, I don't know, 60 seconds and have a go at answering that question. Why? So 60 seconds. So yeah, so Jacob, we have what we call a cis and a trans isomer. So on the fumarate, you've got hydrogen on opposite sides. On the malleate, you've got hydrogen on the same side. So when they would go into the active site, you wouldn't get bonding if you added in the malleate, because it'd be like sticking a magnet in and then flipping the ends of the magnet around, so the positive and positive and the negative and negative. All right, let's jump onto carbohydrates. Everybody's favorite. 2 seconds. Thought I had these. Anyone want to have a go at telling me what a carbohydrate is? So carbohydrate has carbon, hydrogen, and oxygen. Carbohydrates, aside from being delicious, make up most of the world's biomass. I'm going to put this back over on my door. So most of the world's carbon is locked up in plants as cellulose, or when we eat it, it's fiber because we can't digest it. So carbohydrate, we have carbon, we have hydrogen and oxygen. So carbo is carbon, hydrate is water. So carbon, hydrogen and oxygen. Again, most things in organic chemistry are fairly logical. So, general formula, and definitely write down. So you've got H2 and then you've got whole numbers of C and H2O as well. So all of this stuff is linked together. We have monomers of carbohydrates that make up the bigger molecules like starch, glycogen, table sugar, and stuff like that. So monosaccharides are the monomers that make up the bigger carbohydrate molecules that are also polymers. So monosaccharides, crystalline, white, they taste sweet, and they're very soluble in water. So what kind of bonding do we like when we're trying to dissolve something in water? Any ideas? So we need to have hydrogen bonding. And we have that in spades on the carbohydrates. So definitely write down this molecular formula. So C6H12O6. glucose, galactose, and fructose. They are all isomers of each other. So 3 structures are here. I'm not going to make you draw them because you can draw them in your own time. So the thing to remember here is I'm going to give everyone 60 seconds to actually demote is even turned on. No, I'm looking at. What's the difference? I mean, there's obvious difference with fructose, but what is the difference between glucose and galactose? Can anyone see it? Think about malleate and fumarate. So Jacob, the monosaccharide formula is C6H12O6. So all these 3 have the same molecular formula. What's the difference? I mean, obviously fructose is completely different, but glucose and galactose, anybody spot the difference? I would definitely want to be able to do this before your exam. That's one thing. So, well, I should probably tell you the difference. So the difference here is we have a cis isomer here. Over here, we've got a trans isomer. So the hydrogens at carbon 1. So we've got cis isomer, and then we've got trans isomer. And then fructose is obviously completely different. So we've got these, what they call chiral carbons, meaning all these carbons have 4 different attachments, and this is where we can get rotation of the OH group and the H plus. So glucose and galactose have 5. We count 1, 2, 3, 4, 5. And remember, we have isomers of glucose now. So we have alpha and beta glucose. So, sorry. So alpha glucose, we've got on the carbon 1, the hydroxyl group is facing down. Beta glucose, the hydroxyl group is facing up. Then we have a straight chain form, just to make it a bit more complicated. So we have beta glucose, alpha glucose, then we have the straight chain form. Now, I'm not expecting guys to absolutely nail this in one go. There's quite a bit to understand. We have an equilibrium between the three. I think it's 99%, I always get this mixed up, exists as alpha and beta, and then you have this intermediate form, and we can shift between these two forms of glucose. So solubility, we remember that hydroxyl groups are extremely polar. So they will bond with water. So, I mean, you've seen how much sugar you can, I don't know if you've done an experiment, but you can see how much sugar you can dissolve into water. It's a huge amount. So remember this, like dissolves like. Okay, so when we put carbohydrates into solution, 99%, yes, I got it right this time, I didn't say the wrong thing, exists as either alpha or beta. You can convert between the two, but they have to go through the intermediary form. Which is the straight chain. And now we're going to the straight chain form. So this takes a couple of goes and a little bit of research. So this is quite a broad overview of all of it. But we either have an aldose or a ketose. So if we remember back to our functional groups, the aldehyde sits on the end because it's attached to hydrogen. Ketone, we have a carbon to oxygen double bond. Which sits between two other carbons, so not on the end. You might see this drawn a couple of different ways, but it doesn't really matter. So, okay. Is everybody following for now? It is a quite complex topic. But it shouldn't be any more difficult than the others. It just, there's a bit more to it. So polymers. So we can take monomers of carbohydrates and stick them together to produce polymers. Shock horror, right? So again, very logical. Disaccharide, 2 monosaccharides. Polysaccharide is 3 or more. So table sugar. Now we remember we've got different kind of bonding, but it's all the same. This is just, what you're seeing here is just a condensation reaction. So we take glucose and fructose, the OH and the OH groups, like our esters and our proteins. We get a reaction here where we get what you call a glycosidic bond, where we have oxygen on either side. Sorry, we have oxygen and a single bond to carbon on either side. And we also produce water because we have OH and OH. One H from here, the HO from here reacts forms water, and creates a glycosidic bond. So that's our disaccharide, again, table sugar, as simple as it gets. Then we go down to our polysaccharides. The monosaccharide is glucose, disaccharide is glucose and fructose to make sucrose or table sugar. We then have starch. Starch is what plants use to store energy. It's what makes your, what's the word? It's what makes your water all gluggy when you cook pasta, when you cook potatoes. It's the starch breaking down. Glycogen is what's stored in our muscle cells. So we store glucose in our muscle cells for a quick hit of energy. Cellulose is what makes up plants. So cellulose is indigestible to humans. Undigestible, whatever you want to call it. So plants store their sugars as alpha glucose in starch. We also have amylose, which is starch where the glucose is arranged in a linear fashion. I would make note of this. Amylose is linear. Amylopectin, and again, just like with our hydrocarbons, amylopectin has branches. So amylopectin, we've got our linear molecule, but then we also have branches of glucose coming off, and they're all linked by this glycosidic bond or oxygen. So amylopectin. Oh yeah, that's already talked about that. Okay, so again, amylose, amylopectin form from the same condensation reactions as before. So hydroxyl groups are in the same position. That's how we get our linear molecule. So cellulose, and part of the reason we can't break down cellulose is because we've got beta glucose, and we have long polymer formed by this beta glucose. So you can't eat cotton because it's 100% cellulose. Most plants have some level of, okay. This is the part of food that we call fiber. So anybody tell me partly what the difference is here between starch, which is here, more in the orientation of the CH2OH groups. What do you see that's different? Anyone? So you've got in starch, now the lovely serenading from the screaming toddler. So in starch, you've got linear, they're all on the same side. The reason we can't break down cellulose is because you have alternating sides, and the enzymes that we use to break down starch can't break down cellulose. So we can create enzymes, and there are certain strains of yeast that we can use to break down cellulose. Cows can break down cellulose, but we can't. We also then have glycogen. Now, glycogen is a long chain molecule, but you can see here we use it to store glucose. It's not, we don't actually have to break down glucose, break down the amylopectin. We can use it in its long chain form. Should make it not too bad time. I should get through plastics as well. Okay, so and I'm going to send these slides when I upload the recording after this. So we have the common carbohydrates, glucose, fructose, and galactose, with the monosaccharides, maltose, sucrose, and lactose. And then the polysaccharides are glycogen, starch, and cellulose. I'm going to get you guys to do this. We can go through it. Now, jumping around a little bit, but it's all the same stuff. It's all just polymers are made up of different monomers. And we can apply the same logic to carbohydrates, proteins, fats, and now when we look at plastic as well. Just let me find it. That's macromolecules, why can't I find it? Okay, there we go. So we can apply this same logic of monomers and polymers to plastics as well. We have monomers of plastic that are formed. We get a reaction. We create a long chain of polymers. And this is, I mean, I would say like 20% of this unit can be summed up using that. We all know what plastics are. We've all got some probably on our desk. Have I got any here? No, I can't find plastic. A phone cover, a very flowery phone cover. They're quite easy and cheap to make, but that is also, they're also a massive problem. But again, we take monomers of ethene effectively and join them together into a long polymer molecule. If I can, I'm not looking out. What we do to make plastic is we take ethene, we add them together to produce polyethylene, or polyethylene as it's more commonly known. And we can do this effectively forever. We can make as many as we want. We've got, I mean, ethene, it's the monomer polyethylene. You just add poly in front of it. We break the double bond in the ethene molecules, and it produces a polyethylene segment. That can be 10 molecules, could be 100,000, anywhere. I mean, you could theoretically just keep adding them on forever. So we have low density polyethylene. So when we put ethene together, you can make it cheap and nasty, crank up the pressure and temperature, and effectively melt it together. This is fine, but it produces short branches. If we're thinking about intermolecular forces, what impact would the branches have on this polymer? Take 60 seconds to have a think about it. I'm just going to make sure this dog isn't got out. So the branching will create weaker plastic. It sometimes has its place, plastic drinking water bottles. And things where you need soft flimsy plastic. So because we have the presence of branches, we have less dispersion forces because the molecules aren't as tightly packed. So we get soft and squishy plastic. So sometimes it's cheap and nasty. Other times it's done for a reason. So low melting point, it's not very dense, it's soft and squishy. So we can actually, crystalline is how consistently packed a molecule is. So for something like table salt, it's pretty much perfectly crystalline, hence why it's crystal. But plastic is not very crystalline and is not a conductor of electricity. Now you're looking at me going, you can't have plastic conduct electricity. We can now. Okay, so we have high density polyethylene. So this is the good stuff. It's produced using a catalyst. We know that if we use a catalyst, we can use lower temperature and lower pressures. Well, that more comes in industrial chem next to it. Because the conditions are milder, it forms slower. We get less branches. Has a higher density because of the tight packing. It has a higher density. It's got increased hardness, like my phone case. You can actually get crystalline segments, so you can actually produce electricity that conducts, produce plastic that conducts electricity. And it has a really high melting point. Because we know the higher the intermolecular forces, the higher the melting point. So we can now produce what we call ultra high molecular weight polyethylene, whatever you want to call it. And we know, if we go all the way back to the boiling point video 10 weeks ago now, the more dispersion forces between the two molecules, the higher the boiling point. The stronger the intermolecular forces, the harder something is. So we can now make bulletproof vests that are made out of plastic, hip joints, helmets, boats. You can get boats that are made out of ultra high molecular weight polyethylene, and they can go through anything. They will not break. You can basically drive them into anything and they will hold together. So the big difference here and the takeaway that you need to know for your exam is the extent of the branching. High or low density polyethylene what do we got? We've got branches because it's produced under high heat, very harsh conditions, forms very quickly. HDPE, so we can use this for buckets, pipes, PVC, fuel tanks. You used to make fuel tanks out of metal. I mean, you can see why that's probably not the best idea. You can now make them out of plastic that won't break down under the harshness of the petrol. So, again, I would just take 30 seconds, time, and draw these two. So this is LDPE. We've got branches being formed. HDPE, we've got limited branches or very small branches being formed. So I'll give everyone 30 seconds to draw that. It's not just the extent of the branching, but it's how we can actually control the branching. So now we can use propene and make polypropylene. We can actually control the way the branches form and how the regularity at which they form. The more regular the methyl groups are attached, so alternating sides is always best, the tighter they'll fit together. So the tighter they fit together, the higher the intermolecular forces. So here we've got 3 different kinds of polypropylene. So we have isotactic, atactic, and syndiotactic. So isotactic, all groups are on one side of the polymer chain. So you've got hydrogen, CH3. So this is what we make most of our plastics out of now. We can also make thermal underwear out of it. It's a very good insulator. Baby bottles, our banknotes are now made from them as well. So atactic, this is where we get random distribution of the side chains. So the side chains might be short, but they are randomly distributed. Syndiotactic is where we have regularly alternating sides. Now, this is something that we've only just managed to successfully produce. These slides are 12 months old now, from last year. But now it's being used to make car parts that will replace metals. It's being used for bulletproof cars. It can conduct electricity along its entire length. And it can actually take quite a bit of electricity because of its high melting point. So now we could make power lines out of plastic, wiring out of plastic. I learned chemistry first time like far too long ago, 20 years ago. So I started doing chemistry in grade 8. And there was no way that any of this stuff was even comprehended. Okay, so now we're looking at, how are we doing for time? That's about, actually, we'll finish in an hour. It's quite a bit to get through. So when we have plastics, we have polymers, right? And they're all made up of monomers. But what we can do is create other organic molecules by changing the functional group. Now remember, all the way back to the very first slides, we classify the organic compounds based on what's attached. So we change what's attached to our polypropylene and we get completely different products. So we can create polypropylene. So that's just polypropylene. It's cheap. It's quite durable. It's hardy. AstroTurf is what we make out of that, I think. Yep. So all your ropes. If we take everything off the outside and we replace it with fluorine, we get Teflon. Jacob, I think we've talked about this before. Why does nothing stick to fluorine, to Teflon? And we use Teflon for non-stick pans, non-stick cooking implements. So what normally happens when you're cooking is that you'll burn food. Food that's burnt will react with the metal and it will quite literally stick to it. Fluorine is the most reactive element. So once it's stuck onto those carbons, nothing else is going to take its place. And in order to stick Teflon onto a pan, because it's non-stick, takes a very long time. They have to scratch the pan, put a layer on, scratch it again so it fills the gaps. It's really quite a process to stick a non-stick coating onto something. So we have dichloroethylene, which is glad wrap. So these are all plastics, they're all polymers, but we alter the monomer that we're sticking together and we're altering the properties of the plastic that's produced. So acrylic or polypropylene. So we've added a cyanide group. There's people getting fake acrylic nails, sticking cyanide under their fingers. So fabrics, all of our clothes have polypropylene in it. So polystyrene, the scourge of the earth. Because it will just about never break down. And it's used in packaging. Okay, the coolest, I think one of the coolest things is that super glue, when you stick it on something and it comes in contact with the air, it actually forms a plastic. So inside the tube, it's just liquid, nothing will happen. Once you open it, you stick it onto your hand, whatever, it's going to react with the water and produce a polymer. The water is the catalyst for all of the methyl cyanoacrylate to polymerize, and if you stuck it to your hand, it will make a plastic with your skin and be very, very painful and difficult to pull apart. So we add a methyl group and an ester, and we get Perspex. So just by changing the functional group that's present on our monomer, we can produce a completely different kind of plastic. All right, we just went through a lot then. Thankfully, the toddler stopped screaming after a while. I'm going to just upload this. I'll send it out tonight with the slides for carbohydrates. So the questions there, they're all practice exam questions. They start easy and they get harder. Next session, we will just do practice exam questions, probably from 2020 and 2019 as well. So although the ATAR system has changed, they're still using the same content from 2019. So that will probably go through another year or two before they change anything, and they won't really change much. So